on this is recording. She works a lot on the topography and plate tectonics of planets, and she is interested in the relation between what the shape is of planets compared to the distribution of lands and oceans. So, the floor, as a reminder, please keep your video on, and if you have any questions during that talk, please put them in the chat, and one of the organizers can ask them. Yeah. So today we're going to have a very interesting talk, I think. So the floor is yours.
Yeah, cool. Thanks very much. Yeah, so I'm Claire. I'm a PhD student in Earth Sciences at Cambridge. And I found myself working with theoretical planetary science. So I spend most of my time fiddling with models to see if they can be applied to un-Earth-like conditions. And the subject of this talk is our incorrigible use of topography towards answering whether or not most low-mass planets should be covered in water. And the spoilers is kind of hard to answer, but we can put some bounds on it if you believe the models. So I've been thinking a lot about what topography could be like on exoplanets. And I don't have loads of friends in doing this. In fact, I'm usually asked why I do a PhD in this planetary topography. Well, topography interacts with lots of aspects of the planet as a system. But one very basic thing it does is raise up land above hypothetical sea level. So for planets with surface liquid water, regardless of how likely that is, higher topography means you can store more water on the surface before the planet is completely flooded. And if I'm practically a sphere, then even a little bit of water will turn me into a global puddle. You probably know there's a lot of tension on how likely water worlds are versus land planets versus something in between. And in this talk, I'll try to argue that topography might be a neat way to approach this question from the theoretical side. And of course, the other factor influencing where a planet is on this line is how much surface water it actually has, which is probably quite hysteretic and stochastic and tricky. Meanwhile, it is in fact tractable to physically model some components of topography from planetary bulk properties. So when I say modeling topography, I don't mean I'm reproducing Earth down to the last detail. You probably know Earth's topography is bimodal. So this case is a direct result of plate tectonics, and that's this upper subplot here. We only have, we have one mode corresponding to the crust of oceanic plates and the other to continental plates. But we don't really have a clue how common plate tectonics is on rocky planets, despite a lot of serious effort. And Venus is an Earth-sized planet with no obvious plate tectonics in the present day. It's hard to say if it did ever in the past. And Venus's elevation looks something a bit more Gaussian. Actually, I don't know if you can call this Gaussian, but it's definitely unimodal. You probably know Mars is a different story, and Mars is kind of weird topography, mostly likely has to do with some degree 1 convection, and that's a whole another story we're not really going to talk about today. So we aren't going to look at anything as complex as bona fide continents. The evolution of what's on Earth is not properly understood yet either. And it's not guaranteed that all planets will have continents made from different material than the rest of the planets, like Earth's granite continents today versus the basalt seafloor. And of course, because if we are relaxing the assumption of plate tectonics, we are not going to have these dramatic collisional mountain belts. So whether or not you have that, or lots of magmatism, volcanism, or anything, there is a pretty certain bet that a planet will have something called dynamic topography. And if you haven't heard of dynamic topography, I literally hadn't either before I started my PhD. But then I learned that it's actually a pretty interesting phenomenon. So dynamic topography is the direct surface expression of mantle convection. It's pushing the lithosphere up or pulling it down. And we have dynamic topography on Earth, although it might be easy to miss because it's only about 1 kilometer high. And these maps are showing Earth's observed dynamic topography at different spherical harmonic degrees, aka different surface length scales. So in the high frequency one on the left, it looks a bit messy, but if you look at this low frequency filter on the bottom, it pretty clearly shows topographic rises above where we know there are mantle plumes, like Iceland and East Africa. So if we're thinking about the physical forces that cause this dynamic topography, there's 2 components and they go hand in hand. First, we have the stress from the mantle flow itself, which creates tractions on the base of the lithosphere. But this component is actually a bit smaller than the other one, which is the fact that a hot upwelling plume is less dense due to thermal expansion and the thinner lithosphere right above the plume. So this negative density anomaly means that the equilibrium surface floats a little bit higher compared to the surrounding area. This is pretty analogous to area isostasy, which you might have heard of, where that, when you talk about that, we're usually talking about composition differences that cause the density, or here we're talking about temperature differences. So that is really all there is for dynamic topography. It's not super complicated. When I say dynamic topography, I mean both of these phenomena together, and there's no use separating them. And just for interest / completion, I'll mention these other 2 ways of making topography on stagnant mid planets that probably also important, but we're not going to model them here because they're just a little bit complex. That is, they require information that is kind of difficult to justify having for exoplanets. So on the left, you have this hot mantle plume partially melting. And because melting is selectively extracting different minerals from the solid mantle, and these tend to be lighter, so the resulting igneous rock is less dense than the mantle. And this is also kind of isostasy, and it wants to float up. And that's on top of piling just a bunch more lightweight material on top of the lithosphere. And then on the right, you have a kind of opposite where positive topography is created above the cold sinking bit of mantle this time. So here we are giving the lithosphere some non-infinite viscosity. So the lithosphere itself is getting pulled radially inwards towards the center of the drip. And this convergence of lithospheric material creates the topographic rise. It's just being kind of smushed together. And both of these mechanisms have been used to describe certain features on Venus. But because, at least for this magmatic thickening, we need to know details about the thickness of the crust, which I'll get into a bit later. It's not super viable to try to predict right now. But anyways, back to dynamic topography. So the important thing is the amplitude of this topography is directly extracted from 2D or 3D numerical models of mantle convection. Because these models already calculate the stress and the density in the convection, then we already get the dynamic topography for free, because these are just all the components that you need to quantify. So to the first order, dynamic topography doesn't really have anything to do with the crust. You don't even really need a bona fide crust being like a compositional thing, because the crust, the thickness of the crust and its mineralogy or lithology is the result of partial melting of the mantle, like I just mentioned. And it's very tricky to make predictions about this, even though like geochemists like have thermodynamic models that they use to study melting on Earth that can be quite sophisticated. But the problem is that the most sensitive variables are things like the temperature profile near the surface. And we really just don't have a good clue what that is. So it's not really worth using these sophisticated models to say anything about the crust thickness and composition on exoplanets, at least at the moment. And so the minor inconvenience is that running these 2D or 3D numerical convection models to calculate dynamic topography can take a few months on a normal computer, or even like 24 cores or something. So we're interested in exploring how dynamic topography changes with a wide parameter space occupied by exoplanets. So to get around this, we'll need to extract some scaling relationships of dynamic topography from just a few big models. And then we can plug these scalings into 1D convection models, which run in seconds. And then we can estimate the size of ocean basins of very simple planets, which are shaped only by dynamic topography. So this might be an oversimplification or a kind of like low ball for the topography, but the point is that it's definitely ubiquitous and it's very straightforward, relatively speaking, to make these predictions. So I'll say something about what 1D convection models do. And sorry if you're familiar with this already, but convection is really good at redistributing heat. So the interior temperature profile of something convecting is basically constant, except for near the boundary layers at the top and the bottom, where the temperature gradient looks more like something that's conducting heat. And it can be shown that the thickness of these boundary layers goes with the Rayleigh number of convection to the negative 1/3 power, which is this non-dimensional number here. And the Rayleigh number essentially describes how vigorous or how turbulent the convection is. So in 1D convection, you just need to write a few ODEs that describe the conductive heat flux across the top and bottom boundary layers, and then you can track the temperature of the system like that. So at face value, the Rayleigh number will increase with the planet size because of this cubic dependence on the depth of the convection, Z. So we can just say that's the mantle depth, or planet radius minus the core radius, everything else being the same. And for simple constant viscosity convection, the Rayleigh number is the only parameter that you need to describe the whole system. But technically, we're in the stagnant lid regime, and that's one extra step. So here's stagnant lid, although usually people say this to just mean like the opposite of plate tectonics, like a planet with no plates. It actually has a technical meaning in mantle convection, which is something that you get naturally when you have a viscosity that increases with cooling temperatures. So that means at the top of this box where it's cold, the viscosity can get so high because it goes down with the cooling temperature that the material virtually can't move at all. So it's not even participating in convection at the top. And this is different from planetary crusts, which are a compositional distinction. We get crusts are made from different material. This is the same material as the mantle. We'll have the same properties, except it's just a high viscosity at this temperature. So you can imagine that if the strength of the viscosity dependence increases, then the stagnant lid will grow because it will, the low viscosity will, or the high viscosity will extend to lower depths. So this is an important parameter. And so yeah, to describe the system, you need to know the Rayleigh number and the viscosity contrast from the top to the bottom. And what I mean by describe the system is that convection is scalable. So for two systems that have the same Rayleigh number and viscosity contrast, they will follow roughly the same behavior, even if one system is golden syrup in a tank and one system is a planet. In the stagnant lid regime, appropriate for mantles has been isolated to a certain range of Rayleigh numbers and viscosity contrasts. So what we want to do is run simulations in this area, like this. And this is worth mentioning the model setup for those of you who are interested in this. So it's just a 2D box, an 8:1 aspect ratio. So it's extra wide, so that way we're able to capture the natural width of convection instead of forcing it to be like a 1:1 aspect ratio. And we have
I'm sorry to enter. I'm sorry, there was a question from the audience are you referring to potential temperature being constant, since temperature not constant in, for example, atmospheric convection?
Yeah.
That was just a quick question from the audience.
Yeah, sorry, that was going back a couple of slides. Just, I'm used to thinking of convection as being something that equalizes entropy or potential temperature, not temperature itself.
Mm-hmm. Yeah, sorry. Yeah, there's a potential temperature.
Okay, thanks.
So like the actual temperature, obviously it gets hotter with the high pressures. So yeah, thanks. Okay, so we can run these convection models, and we get some nice animations when we do that. So you're looking at the temperature field of a single 2D numerical run, and then we get this dynamic topography on the surface. So I exaggerated the Y scale here, but this is just to see that the dynamic topography directly follows the convection. So the hot upwellings are the white areas coming up from the bottom, and they have positive topography. And then the orange drips from the upper boundary layer have negative topography. And this dashed line is the root mean square amplitude of the topography. And that's what we want if we're going to try to apply this to 1D models where you don't get a horizontal dimension. So we did 9 production runs varying Rayleigh number and the viscosity contrast. And then, again, these are the 2 main scaling parameters. So that's all we really need to know to describe the system. And then we fit the scaling relationship. So we get what we expect. Let's just look at this one first, which is that the larger Rayleigh numbers can support less topography because they have thinner thermal boundary layers, and this has less scope for thermal variations. So you see that the scaling, it's a bit weird, it has like this inflection point, which we didn't expect and hasn't been seen before, I think, but it is robust. And we are explaining this with the fact that higher viscosity contrasts lead to a thicker lid or lithosphere. So this also works against the thinner thermal boundary layers. And then we get to do a bunch of 1D models. So we are free to do thousands of runs. So we vary some unknown parameters randomly in a kind of Monte Carlo style, namely things like the viscosity activation energy, which won't be known. And again, we get the result we expect, which is lower topography for more massive planets. Actually, you'll see it's very low. It's for the kind of most massive rocky planets that are still rocky. You get a RMS topography of like 20 meters. So it looks like these planets are at the minimum essentially just kind of smooth ellipsoids with very little variation. Okay, so with that, we have the scalings estimate the dynamic topography RMS, but we can do a bit better. So I will spend a couple of slides justifying that we have enough information to expand this scalar back to 2D. So let's look at some spherical harmonics to do that. So above degree 5, Earth's topography power spectral density is nearly a straight line in log-log space. This is saying that for any distance scale I look at, the differences in altitude, or more generally, the statistics that describe them, change in a predictable way defined by a power law. Now, there have been a number of investigations in the past searching for some universal value of this slope of the power spectral density with the wave number in log space. And while the people were saying it was around -2, and What's interesting about that is the spectral slope of -2 means that topography is red noise. So it follows the statistics of red noise. And this kind of relationship describes a fractal pattern. So since Mandelbrot introduced fractals to geoscience about 50 years ago, people have started seeing them everywhere. And they've been used in films and video games, starting with Star Trek, The Wrath of Khan, actually, to create realistic looking landscapes without having to manually fill in every little slope. And since this first came out, there have been a number of investigations into the fractal scale invariant nature of planetary topography. And it's now understood to be much more complicated than this simple fractal described by one power law. It's pretty well described actually by something a bit more mathematically scary called a multifractal. And this just means that your planet can, in effect, have some regions that are plains and some regions that are more rough, but still be described by this unified statistics. So the statistics are not spatially homogeneous. And this is more just for fun, but I thought it was really cool. So here's some recent work on the multifractal properties of solar system topography by Francois Landais, where the 3 parameters in this table are just the parameters you need to describe the statistics of multifractals. The actual meaning doesn't really have a physical meaning and it's not super important. But what I want to point out is that these planets, which are geodynamically active and have atmospheres, so that's Earth and Mars, have very similar values of this one parameter. And it turns out that if you kind of work through the maths, this H parameter being 0.5 is equivalent to this slope of -2 that we had from the original work onto monofractals. So that's kind of interesting because it validates this whole simple model of just topography being red noise in an empirical sense. And even though you can do more complicated representations. And then meanwhile, the Mercury and Earth's moon, which are geodynamically dead, and the only topography is really going to just be from impact craters, have this different value of H. So there's a suggestion that the slopes of the power spectra of planetary topography may be somewhat universal and predictable. So yeah, I won't use this multifractal model. I'm going to use something simpler, but I wanted to put this up because I think it illustrates this point really well. So I'm looking at dynamic topography specifically. So what I actually did to be self-consistent with pure dynamic topography is extract the power spectral densities self-consistently from my own numerical convection runs. And I also found that they shared a characteristic spectral slope within the noise, if you believe this top right figure where they kind of look like, I mean, they bounce around a lot, but roughly it's the same slope. So if I know what the spectral slope of dynamic topography should be, and I can calculate the RMS from my 1D convection models, then I can reconstruct a whole spherical harmonic representation of the surface of a planet just from a 1D model. And basically what this means is we're generating like synthetic DEMs, digital elevation models of planets. And although this method is for dynamic topography that I've been doing, in principle, if you know how the root mean square of topography should scale, then you can give any kind of topography mechanism the same treatment. And it might even be justified to just say that it's red noise and it has this slope of -2 all the time, because that would account for like empirical modification from erosion. So all these maps are for identical planetary conditions, and therefore they have the same root mean square elevation, even though they look different from grid point to grid point, because they have the same statistics. So if we integrate these maps from the surface to the highest point, then we will get an identical volume of the ocean basin. So that's this here. And this is what I said I was going to try to estimate. such as the ocean basin capacity associated with pure dynamic topography. So I'll walk us through this plot because there's a bit of interpretation. So these swaths are scaling for this integrated volume underneath the highest points of the dynamic topography for different slopes of the power spectrum. So this is the pure dynamic topography that I extracted, and then this red noise. And you can see that they're not very different, and that's because at the low degrees, they're roughly the same behavior, and that's kind of where it matters. But this is only going to be useful if we compare it to some actual amount of water on the surface, right? So here we just did the most simple scaling we could think of, which is that the ocean is a constant mass fraction of the planet. And this is like saying Earth has one Earth ocean of water. So a 2 Earth mass planet must have 2 Earth oceans of water. And astronomers do this kind of thing all the time. So it's useful to contextualize it like this. And these contours are just different assumed values of this constant mass fraction of ocean. And because of how surface area to volume ratios work, a constant ocean mass fraction means that the resulting volume of water increases very quickly as the planet radius increases. But then, meanwhile, the maximum ocean basin capacity actually decreases with planet radius, despite these much higher surface areas. And that's because, like we saw, these massive planets are smooth and round and very little topography. But then in general, the way to kind of use this plot would be if any mass, say if I take 1 Earth mass, any ocean mass fraction contour above the value of the topography scaling is going to make a water world. It means it's going to be flooded by that amount of water. And if we want to get a water world limit from this plot in terms of planet mass, we just pick an ocean mass fraction we're interested in, follow it until it intersects with topography scaling. And then that gives us the largest planet that could maintain land with dynamic topography alone. Here is just quickly some different radiogenic heating budgets. So this is the minimum that you'd expect for the inferred distribution of uranium and thorium in planet hosting stars. And the solar system is kind of in the low end, so there isn't a big difference. But if we look at planets with high uranium and thorium budgets and lots of internal heating, the dynamic topography is distinctly lower. And we'd attribute this to hotter mantles having lower viscosities and higher Rayleigh numbers, so they have less scope for topography. And here is another way of plotting the same limit, but with the solar system planets for context. So again, we can predict the hypothetical water world boundary, which is the maximum amount of surface water that would flood a planet. And the actual ocean basin capacities of Venus, Earth, and Mars are calculated from their known topography, and that's higher than pure dynamic topography because these planets have other topography, of course. So that's the amount of ocean that real Venus, Earth, and Mars would need to have before they became water worlds. Obviously, they don't have any ocean, but that isn't really the point of this. So down here is the actual mass fraction of Earth's ocean today, also for context. So obviously, dynamic topography is a lower limit to the true topography. And maybe you want me to talk about some more realistic limits. So the question is, what controls the ultimate height of mountains? And Harold Jeffries tried to do this in the 50s. Here he is haunting the building I work in. So I have to mention him, even though he lost some credibility because he was an early detractor of that new theory of plate tectonics, which just was never going to catch on. And regardless, Jeffries found that to support a topographic load equal to the hydrostatic pressure of rho GH, somewhere in the lithosphere underneath the load, there is a minimum stress of 1/2 to 1/3 times this weight of the load. And this prefactor comes in from the way that elastic stresses are distributed, but takes a very narrow range for all sorts of load configurations. So if it's a triangle or a rectangle or a sine wave mountain, it doesn't matter. The slope doesn't matter. You still get this result where it has to be a stress of 1/2 to 1/3 times the weight. So in other words, if we balance this hydrostatic pressure as at the maximum topography, is H max, with a finite strength of the crust, then we get an expression for H max. And we can even test this with some rough estimates of the strength and density of granite. And using this prefactor of 1/2, we actually predict the height of Olympus Mons and Mount Everest quite well. And I forget why I didn't show Venus actually when I first made this slide, but I think it actually just overlaps Earth because the maximum height of observed topography on Venus is very close to Mount Everest. It's a little bit higher actually. And the problem is that this isn't actually so simple because it comes down to Y, the strength of the rock, and we don't really know what Y is. Like this 100 MPa kind of back of the envelope calculation happens to work, but this is only 3 planets, and there's lots of things that actually go into determining what this would be if you tried to. So in particular, the presence of water in the crust and the geothermal gradients of the temperatures and existence of other fractures will really alter what Y is by like factors of 2 or 3. So maybe this will be worked on a bit more in the future, but I'm going to leave it here just as this rough guess. And another issue with the crust strength thing is that it doesn't actually tell us anything about how topography is made, just that over a few billion years we pretend stuff happens, and now maybe that's fine, but I will suggest that the second easiest way to build topography on stagnant lid planets is with volcanoes. So volcanoes are probably ubiquitous on exoplanets, especially hot stagnant lid planets, because heat needs to get out of the mantle. And I'm not going to go into lots of detail on this, but it's possible to make some simplifying assumptions about how volcanoes work, and then write up parameterization for the maximum height of a volcano. So constructing an edifice with magma requires bringing magma from to the surface from depth, and that needs to maintain a positive pressure gradient from the magma chamber underneath the surface to the top of the volcano. And then as you pile more and more lava on top, and stuff needs to travel farther up, and it's harder to maintain this pressure gradient. So I don't know how useful this is, because it also depends on, even though it's like a simple equation, the values of these would be quite difficult to actually put some bounds on. Like we have to know how deep we expect magma chambers to be. And there's actually arguments that this is, they take a very similar value for Earth, but this hasn't been studied for other planets. And also this critical eruption pressure, delta P. And that once again comes down to the rock strength, because it's just like the tensile strength that, or the tensile stress that would crack the roof of the magma chamber. And I just wanted to tell you about this because it kind of paints the whole picture of topography, but we're not going to use this one. Okay, so let's go back in time a bit to this plot. And then let's add this crust strength approximation to the true maximum topography, which is not very rigorous, but is better than nothing. And then some more stuff. So here's some planets around TRAPPIST-1. And these data are current observational estimates for the amount of water they have from Eric Engel and others. And these different estimates kind of span the whole y-axis. And that's because, as you may know, it's not really practical to measure water fractions in space. If we just have bulk density to go on from planet mass and radius, then we assume the planet has 3 layers, being iron core, rocky mantle, and a volatile layer. Then the relative masses of these layers are degenerate. But it looks like unless the core masses were really small or not present at all for the TRAPPIST planets, they have low enough densities that they're consistent with too much water, even for the theoretical peak topography, if they're made out of something that has a crushing strength of 100 megapascals, which is, who knows if that's correct. But there are other interpretations of these low densities. Like, I don't think this paper considered light elements in the core, And we definitely don't know for sure what's going on. But well, maybe in the future we'll fill this plot in a bit better when you guys find more planets. So in fact, as you probably know, there's lots of small exoplanets whose observed bulk densities are much lighter than an iron rock mixture. And from what we know at this point, it seems like these volatile rich planets are fairly common, or at least findable. And I think the takeaway from this figure is that you only need a few tenths of a weight percent of water for the kind of Earth mass regime to make a water world. And then sub-Earth mass planets will be the most likely to not be water worlds. And we already kind of knew this or could intuit this, but I think this has been my start at approaching this limit with some quantifiable geophysics. So that's the topography story. And for the last 10 minutes, I might try to take some time for a little coda. So I'm going to turn to the thing pulling against topography. That's actually how much water is there on the surface of the planet. And we can break this down into the influence of the total water budget and the influence of the relative flux of volatiles from the mantle to the surface. And if just tenths of a weight fraction of water will make water worlds, then can we use some more earth sciences to look at what kind of say the planet itself might have in this? So we're going to swoop in from the top here and notice that several oceans worth of water could be inside the planet. So we can apply some ideas for Earth's history of interior water and the physical limits to water storage. And the practical reason why I want to do this is that the modeling to do this for the most part already exists. So whether or not we believe it is different, but there is a precedent. So what do we actually mean by the water capacity of the planet's interior? Well, we really mean hydrogen and OH, which can show up in defects in the crystal structure of the minerals. So when I say something like MgSiO3 saturated in water, it's not literally H2O. This is just shorthand for H2O equivalent in hydrogen. So there are proper like hydrous minerals that contain much more real water, and those we won't talk about here because they're generally only stable at cold temperatures found in the lithosphere, like in subducting plates. And we will ignore these, even though potential new hydrous spaces have been discovered that could be stable in the mantle. So there's a kind of a lot to work on with this. But anyways, here is the crystal structure of magnesium perovskite, aka bridgemanite, which makes up most of the mantle by volume of Earth, and probably most rocky exoplanets of the same size. And then this little black dot is the hydrogen replacing a missing orange dot, aka occupying a defect. So the saturation water of individual minerals can be measured in petrology experiments calculated from mineral physics, and the theoretical basis for this is already laid out, like I said, but I'll mention there's lots of missing data, and me, like other people working on exoplanet interiors, are really hoping for more data. So yeah, so let's just go over this tentative framework I'm going to lay out and justification for the problem. So this is also ongoing work, and this whole section is very preliminary, and I'm especially interested in your comments as long as you phrase them like questions. So is the mantle's physical limit to storing water ever going to be reached in practice? There is fair evidence that many minerals in Earth's mantle are saturated at the order of 1 to 10 ppm by mass. But for molten rock, like in an early magma ocean, saturation is not reached until hundreds or thousands times higher concentrations, or at all if it's even maybe undefined. And this implies that for as long as a little bit of water is brought to the magma ocean planet by impacting planetesimals, which could themselves generate magma oceans, there will be sufficient dissolved water for the crystals that form later to incorporate water at saturation. So this doesn't go into any details about how magma oceans actually freeze, but as long as magma is convecting and the freezing front is pretty slow, I think that the mantle should roughly be at saturation when it cools. And please tell me if this is really a bad assumption. And the next fact is that degassing from the solar mantle is not very fast, especially for stagnant lid planets. And then ingassing is probably not happening at all for stagnant lid planets. So the surface and interior reservoirs are kind of isolated. But then trapping water inside the planet in its early years is convenient if the atmosphere is going to escape. So water ending up in the surface or atmosphere could be irretrievably lost, but water in the mantle will be sequestered into the planet's total water budget and then slowly replenish the surface stock without gassing. So in a scenario where most of the primordial atmosphere's hydrogen escapes, then the planet's entire water inventory would be basically controlled by how much water the magma ocean or the solid mantle could retain after magma ocean crystallization. And this whole view is definitely oversimplified. For example, we know that interior water doesn't guarantee oceans. Like Earth and Venus probably have quite similar mineralogy, but they don't have similar oceans, obviously. I won't really go into Earth and Venus right now because I'm not the best person to explain them. But yeah, so if we accept this whole thing, then how do we go about predicting what water capacities are? So we can compile these for individual minerals, and then you just add them up if you know the mantle composition. And luckily, there's codes that will calculate these mineralogies for you if you tell it the bulk oxide composition and give it an adiabat or a temperature pressure profile. So we do a bit of iteration so the adiabat is consistent with the mineralogy to make these plots. And this might look like nonsense if you're not familiar with mineral abbreviations, but I'll point out the main features. So on Earth, for this modern adiabat of a 1600 Kelvin potential temperature, but the upper mantle dominated by the blue mineral, which is actually olivine. It's green. I don't know why I made it blue. Then when you get to high pressures, olivine goes through a phase change into these gray lines, that's wadsleite and ringwoodite. And that's the same chemical formula as olivine, but different phases. And these two minerals are special because wadsleite and ringwoodite can store orders of magnitude more water than any other minerals for some reason. And then at even higher pressures, we get ringwoodite going through another phase change into silicate perovskite. Again, it's the same chemical, but structurally different. Well, that's the lower mantle. So we can predict these bulk oxide compositions for exoplanets from the compositions of their stars, which are more feasible to measure. And that's because the ratios of refractory elements are to the first order preserved as planets accrete from the solar nebula. So I've replaced Earth's bulk oxides with the raw bulk oxides from the sun. And it's a bit different because we're not accounting for volatilization in this model yet, but you see in sodium especially, which is pretty volatile, it's different. But then on the right, so this is just the mantle of a hypothetical planet around HD 95735, which is just a star I picked from the Hypatia catalog at random. The clear difference is that instead of olivine polymorphs in the transition zone, you get lots of garnet, and that's this green line. And the reason why is if you just look at the bulk oxides, garnet is a big reservoir of aluminum, and this star just has a lot more aluminum. So you can predict it's going to have lots of garnet. The problem is we don't know how much iron goes into the core, so we have to leave that as the free parameter. And that's kind of like a known problem for planetary interiors people. So we can systematically vary the bulk mg to SI ratio in the planet. And this is just the range we see in sun-like stars. We see the mineral composition changes in the upper mantle and transition zone as you get to more mg. So you get to more, you start with orthoproxene and garnet at low mg, and then you move up to olivine like Earth. But then the point is the total water saturation doesn't change that much. It's more like a factor of 2. It's not like a factor of 10. And that's because even though the transition zone minerals store a lot of water, for the most part, the mantle is still perovskite and post-perovskite. And that's significantly more volume in this lower mantle than in these like little narrow bands. So the same water content overall. And the problem is the potential temperature has a bigger effect. So this is more like a factor of 5. And temperature does not strongly affect the equilibrium mineralogy, except for when you see this change in stability here in the yellow curve. So that's ringwoodite changing to garnet. And instead, the water storage capacity parameterizations themselves are a direct function of temperature. So the implication is that because planets cool as they age, the water storage capacity of the mantle will increase over time. And this doesn't actually translate to more water unless you have a mechanism to transport water back into the planet, which the only thing you can really do that with is plate tectonics. But we wouldn't expect infinitely warm mantles either, because the solid mantle can't be hotter than the melting temperature. In fact, the melting temperature could inform the initial temperature we choose for our models, because the first solids form at that temperature. So we'll actually just focus on the potential temperature when the last solids form at the top, aka the melting temperature near the surface pressures. And we can assume that mantle convection begins immediately. There's no prolonged stable stratification. So the temperature profile is instantly adiabatic, but defined by the melting temperature at the top. And this could be reasonable for conceptualizing a mantle that inherits water from the magma ocean as it's crystallizing. So this gives just under 1 Earth ocean mass of water storage for Earth. And that is lower than estimates for the amount of water in Earth's mantle today. But remember that Earth's mantle gets replenished by subduction. So it's feasible that in the Hadean, it contained less water in the mantle. And then finally, this planet size effect is basically just more massive planets are mostly all perovskite compared to Mars here, which is like mostly transition zone. So it can store more like water mass fraction. And then this is the last couple slides. So we get to tie everything together. And let's just pretend that, let's pretend all this water that we sequestered in the mantle eventually makes it to the surface. And I know this isn't true, and I know that it's not guaranteed they will condense into oceans, because that depends on the saturation pressure of the water in the atmosphere. But let's just see how the value we get for like the maximum water available compares to the ocean basin sizes we calculated earlier. And as a kind of coincidence, this minimum water inventory, that's just the hot early mantle added saturation content, is quite similar to the ocean basins from dynamic topography. So we're also showing the basin size you get from rock strength. And that one is definitely safely above all these stars. So yeah, the stars are my guesses for like the mantle water saturation just put onto the surface, which like, I don't know if that will ever happen, but it's kind of a limit. So I wouldn't read into this very much, and it's very preliminary, but the face value interpretation is that even these volatile poor planets, like you might consider Earth to be a volatile poor planet in this scheme of all exoplanets, right? But it doesn't really need very much water to make just this wee little ocean of like half an Earth ocean mass. And whether or not the water condenses, like I said, depends on lots of things that aren't being modeled here. And it would be interesting to see how volcanic topography fits into this, or put more rigorous limits on the strength of rock that can support topography. Haven't found a good answer to that even for Earth, but it sounds like something that you would find deep in the like 1940s journals in your department library. So maybe we can all go have a look. And anyways, thank you for listening. Sorry, I went a bit over time, and I will leave up these conclusions and then take some questions. Thanks.
Thank you for your talk. Everybody can unmute and give a short applause if they want to. Okay, so are there any questions from the audience? You can either raise your hand and ask the question yourself, or you can put a question in the chat and we will ask it for you. Yes, Andrew.
Yeah, thanks for the great talk. Yeah, I'm obviously more of an astrophysicist, but this really makes me want to learn a lot more geophysics. I'm sort of curious. So I guess you showed it again at the end there, those plots of sort of basin capacity. Those, if I understood them correctly, that looks to me like a very narrow range in amount of ocean to where you're not either a land planet or a water planet.
Yeah.
Is this, am I correct in seeing this as a potential fine-tuning problem?
Wait, what do you mean by fine-tuning problem?
Well, just why the Earth has oceans and is not completely a water or land planet. Is it a fine-tuning in the amount of water on Earth?
Yeah. I mean, like Earth is kind
Just
of
because
known
that
to,
red band is so narrow. Yeah.
yeah. Or I mean, wait, I should just explain that the band is the uncertainty. This isn't like the range, or yeah, maybe like this is the uncertainty on this from unknown, like initial conditions and certain properties of the mantle.
Ah, okay. So that,
Yeah.
okay, maybe that's helpful. So what is the range then where you would have oceans and not be, the two limits you showed in the introduction of your talk, either,
Yeah.
right,
Well,
all land or all water?
yeah, and depending on what topography scaling you want to choose, like because dynamic topography, I'd argue, is definitely happening, but it's just pretty low. And then if you can take this purple one that is kind of more like a rogue guess at an upper limit, but we don't know if this is more believable, but it's a lot higher. And then anything below this would be it would be like a kind of marble up until the point where the water mass is so low that it just won't condense in the atmosphere. So I think like Miyazaki and Korenaga did something about this last year, where I think they quoted like 10 to the -5 Earth oceans of water just probably would never condense if once it's in the atmosphere, just because the partial pressure will never get to saturation. So if you can if you want to put like a lower limit on it being a land planet, I would do something like that. But I'm not actually showing that on here.
Sure. Okay.
Does that answer the question?
Yeah. No. Okay. Yes. Thanks for clarifying. I was misinterpreting what the bands meant there.
Yeah. Sorry.
I have more I could ask, but I should let others ask as well.
Yes, so are there other questions from the audience? Oh, yeah, a question from Serena.
Yeah, hi. So as an observer, whenever I look at it, so you mentioned about the atmosphere, but I might not have gotten it clearly. So the mantle is something hard to observe for exoplanets, and we could get maybe volcanic outgassing product to the atmosphere, right? So what would be the most, do you have an idea or suggestion for most sensitive tracer for this? How we could trace what's going on with the mantle? Like volcanic gas, obviously, but I'm thinking of, what can be the best signature to observe.
But for observing what exactly? Sorry.
Atmospheres. So something for these different masses for your, the atmospheric signature that interact with mantle, that would be, I guess, volcanic outgassing. But is there any other, signature that you think it should be good? If we have a really sensitive, good telescope, if we don't have any.
Because even on Earth, like you kind of get volcanic gas and you get like fresh lava, and those are the tracers of measuring Earth's mantle. Like there isn't really anything else.
Did that answer your question, Sven?
Yeah, I think that was my guess, but I was just wondering, I'm just wondering about what should we expect to observe, but I guess I should satisfied with the answer.
Meteorological experimental data.
Let's see, we also have a question from Joshua.
Hi, yeah, thanks for an awesome talk, Claire. I was just trying to understand the difference between your sort of mantle capacity calculations and the recent Miyazaki and Korenaga paper that had sort of 99% plus of the water at the end of the magma ocean sitting in the mantle. What are the different assumptions there?
I think that like 99% value, if I recall right, was a fraction of some like assumed value for the water that was accreted. Is that like,
yeah,
I don't think they were really interested in like the actual amount of water that ends up in the mantle. Because I don't think they were, I'm not sure like what their outgassing model was, but I don't know if they were using like the mantle saturation as something that informed their outgassing model. So like they were mostly interested in how likely you are to form oceans, right?
right. But I think there was some like partition at the end of the magma ocean.
Yeah.
Which ended up in the mantle versus the surface. And I'm just trying to
Yeah.
see how that
So
answer is
for the
different.
partitioning calculations, to do that, you kind of have to assume like a total amount of water, and then you're tracking what fraction of it like ends up in the atmosphere or the melt or the cumulates. And I'm not doing that because I'm not trying to track how much water actually ends up or how much water doesn't go in to the mantle, if that makes sense. Like for any amount of accreted water or delivered water, like the saturation capacity of the mantle isn't going to change. But on the other hand, different amounts of delivered water will affect the total amount of water in the melt and in the atmosphere, or that gets the gas to the atmosphere during the magma ocean crystallization. Does that make sense? Yeah, I'll check again if the Miyazaki and Korenaga paper actually did a parameterization for the saturation capacity of the mantle. I think they just did partitioning. But yeah, that'd be a good thing to check. Thanks.
Okay, and I think there are no more questions in the audience, and we're at the hour. So I would like to thank.
Oh, there is one.
Oh, there's one more question from Vic. Go ahead.
Yes, I'm a geologist, and I'm particularly interested in Mars. You didn't say a lot about Mars. We have considerable geological evidence that Mars had large water bodies on its surface during the first billion years of its history. Mars is very interesting because of that high concentration of water that is in the transition zone. That will lie right near the core mantle boundary of Mars. So that is an optimal way for water-rich material to migrate as plumes from the core mantle boundary to the surface only early in the history of the planet when it's warmer and the heat can be generated by the solidification of the core.
Yeah.
So you didn't say much about Mars, but it would seem that there is a water planet related story under the right circumstances for such a planet.
Yeah, for sure. I mean, yeah, to be honest, I only kind of started this work very recently, so I haven't had the chance to look at Mars, but I really would like to.
I could send you something about that.
Yeah. Yeah, if you can actually, again, and anyone else that is still listening, if you can see my email on the top of this slide, I would love to hear anything. Yeah, that'd be great. Thanks.
Okay. Then I would like to thank Claire again for giving a very interesting talk about geology. Next week we will have we will be back again with the origin seminar. So I hope to see everybody again next week.